Hi guys, my name is Claire Schwapp and this is my final project presentation. So for my project, the data that I found to use was from the UC Irvine Machine Learning Repository and it was under the title Bike Sharing Dataset. The data was obtained from a 2-year historical log corresponding to years 2011 and 2012 for the Capital Bike Share System. The data consisted of information such as dates, seasons, years, months, holidays, weather, and temperature, as well as the number of bike rentals which corresponded to these values. So the question that I set out to answer with my project was which features would help to increase or decrease the number of bike rentals and therefore increase the profit of the company. So that would make the target variable for the project bike rentals. So for the exploration of the data, I used box plots and histograms. The box plots were used to detect the presence of outliers in the continuous data, and the histograms were used to understand the distributions of the continuous data. So here we can see we use the box plot function to create box plots, and we plugged in the columns for each of the continuous columns and gave them a title and stored them in these variables. So these were the box plots that were created, which I'll show soon. And then for the histograms, we used the hist function and did the same exact thing, and these were the histograms that were created. So based on these box plots, we can see that the wind speed, the humidity, and the casual features all have outliers. And these histograms show the distributions of these columns. So the count variable and the registered variables, we can see they seem to have normal distributions. The casual and wind speed variables are skewed to the right, the humidity variable is skewed to the left, and then the temp and atemp variables seem to have something that is called a non-symmetric bimodal distribution. So the transformations that were done on the data set were outlier removal. Dummy codes were created because that was necessary for the regression models. Features were removed from the analysis based on collinearity that was found. There were no missing values, but 10% of the data was removed to randomly pose as missing values. The continuous variables were normalized, and I used min-max normalization for this because min-max normalization keeps the values on the same exact scale for all the features. Based on the results from calling the skewness function on numeric features, it was found that the count and humidity variables, sorry, this is a typo, it's supposed to be HUM, those variables, their skewness was relatively small, and the temp variable, the skewness was very close to 0, so transformations did not seem necessary. For the wind speed variable, the skewness was moderately positive, so it was decided to do a square root transformation on this variable since it is ideal for moderate skews. And after performing the transformation on this feature, the skew became slightly negative, but it was then closer to 0, so it was more normal than it was previously. Regression models assume normality of data, so feature transformation to make sure distribution was as close to normal as possible was important. An interaction term of temp and humidity variables was also created to understand how their interaction had an impact on bike rentals. And then just to show my code of the transformations, this is the outlier removal. Two functions were created and then called on the continuous variables. I did an analysis of correlation and collinearity and created dummy codes, and then I decided not to include some features in the final building of the models based on collinearity that was found between some of them. I evaluated the distribution, Of some variables, I identified missing values. There were none. I still removed a random 10% of the data to mimic missing values. This is the min-max normalization function I created to perform normalization on the continuous variables. And then this was the transformation of the wind speed column that I performed, square root transformation. And then I did identification of principal components, and then I created the new derived feature, the interaction temp hum feature, which was the interaction term between the temperature and humidity variables. So the target variable is a continuous variable, so I went with regression, and the three models that I chose to use were linear regression, random forest regression, and k-nearest neighbors regression. Linear regression because it's simple and it helps us to understand basic relationships. Random forest regression because it's good at handling more complicated patterns and preventing the model from being too specific to our data. And k-nearest neighbors regression because it's able to look at nearby points to understand local patterns. And the combination of these regression models that look at both simple and more complex patterns made it very easy to understand the data well. So to understand model performance, the root mean squared errors and R-squared values were calculated for each model. The random forest regression model had the lowest RMSE, which suggested that it had the best performance of all the models because that represented a very low level of error. The KNN regression model had the second best RMSE with a low level of error, and the linear regression model had the third best, and it had a moderate level of error. Based on the R-squared values, the random forest regression model had the highest R-squared value, which suggested that it had the best fit, and it was followed by the linear regression model and then the KNN regression model. So overall, the random forest regression model performed the best. So here I split the data into training and validation data. This was the creation of the linear regression model, the count variable, and all of the features as predictive variables, and the data was set to train data. And then we plugged in the model to the predict function and the new data as the validation data. And then the same was done for the random forest regression model. The seed was set first to ensure reproducibility. And then the KNN model was called with train, and then the predictions were called. And to evaluate the fit of the models, this is where we calculated the RMSE and the R-squared. So the predictions were subtracted from the count column in the validation data. It was squared, the mean was taken, and the square root was taken for the RMSE. And then the R-squared values were calculated by 1 subtracted by the sum of squared residuals divided by the total sum of squares. And then here are the values that were outputted from those calculations. So how the models were evaluated and validated. After building the 3 models, k-fold cross-validation and hyperparameter tuning was performed in an attempt to enhance the performance of the models, and these actually proved to be slightly successful. The RMSE and R-squared values were used to evaluate and compare the models as well as measure improvements after the k-fold cross-validation and hyperparameter tuning. So the ensemble model function was built to take in 2 arguments, the training data and the testing data. Within the function, the linear regression model, the random forest regression model, and the KNN regression model, as well as all 3 of their predictions, were built and called, and an average of all 3 of the predictions was then taken and returned. The RMSE and R-squared values were calculated from the model to compare its performance to the individual regression models. The result was that the RMSE from the ensemble model was extremely good, especially compared to the individual models. It was slightly higher than the RMSE from the most recent random forest regression model, meaning after the hyperparameter tuning. So the RMSE was not as good as the RMSE from the random forest regression model, but it was much lower than the linear and K-line regression models, so it was better than those two. It was the same for the R-squared value. The R-squared of the ensemble model was high. It was a little lower than the most recent random forest regression model, but it was higher than the linear and K-line regression models, which suggested an overall good fit, but it still wasn't better than the results from the random forest regression model. So the summary and key lessons that I learned, the conclusion was that the random forest regression model performed the best among the three models. So based off of this is the model I would use to make predictions. While the ensemble model did not pass the random forest, it still demonstrated the potential for combining diverse models to achieve robust predictions and improve overall performance for better predictions. This analysis provides insights into the strengths and weaknesses of different regression models and highlights the importance of considering various factors when selecting or combining models for predictive tasks. What I'd focus on moving forward if I were to build onto this project and improve it is I would focus on building on and paying attention to more detail when it came to data cleaning and transformation before building the models to see if that might improve the model performance more than the ensemble model was able to. So I'd really focus on the techniques I use for data cleaning to see how I could improve them, also techniques that I could add to make sure that the data was in the best form it could possibly be in before using it to build the models. So that's the end of my project presentation, and thank you guys so much for listening.